Remember, section 8.4 homework is due tonight by midnight. Being a Friday night, that tends to get forgotten once in a while, so don't take your 5% penalty. Go ahead and get it done. Any questions on any of that?
Is it getting easier now?
Is it getting easier?
Yeah.
I actually think it does. I think the semester gets a little bit easier because you'll start noticing repetition in things. Every day we'll get another type of procedure that we'll do, but it'll be, well, that's just like we did before, only now we change this little thing. So that is a good thing. So if there's no questions over section 8.4, we'll go to section 9.1, which is an introduction to statistical hypothesis testing. And just like we did in chapter 8, this first section of chapter 9 is simply an introduction to the concept. In chapter 8, it was an introduction to confidence intervals. And then in section 8.2, we went, okay, now if we want to do one of these confidence intervals, here's how we do it. So chapter 9 will work the same way. Today is a kind of a concepts, terminology kind of stuff surrounding hypothesis testing. And then on Monday, we'll say, okay, now here's how you conduct a hypothesis test for proportions. Then we'll go to means. And then when we get out of chapter 9, we'll go to chapter 10, which now does 2 sample hypothesis tests. So it's kind of the same thing over and over from here the rest of the semester, just a new twist to it every time. Okay? And everything from here on out can be done automatically using a TI 83 or an 84. We'll show how things are computed, but then we'll bail out and go straight to the calculator. Okay? So, hypothesis testing. And this is also synonymously referred to as significance testing. There is a subtle difference in those definitions, but not worth even worrying about. And we'll start off with having you recall back to your early days in your education. Remember the scientific method? Don't act like you've never heard of the scientific method, because I know I have a 6th grade daughter and she's learning the scientific method in 6th grade science. So remind me what the steps are of the scientific method.
Observe.
Okay, first one is form a hypothesis. Emily and Katie, I have your exams, and I was handing them out a minute ago, and you weren't here yet, but just come up before you leave. Now it's your responsibility to remember, not mine. So first one is form a hypothesis. And what do we mean by that word, hypothesis?
Theory.
Okay, an educated guess, or a theory. It's something that you think might be true, but you're not sure. Well, in statistical hypothesis testing, it's the same thing. We're not sure if this is right or not. We need to find out. So what's the second thing you do? After you form a hypothesis,
Thesis?
you said observe, create a thesis. Okay. Usually I see it written this way: design an experiment. Design an experiment that will test that hypothesis. Step number 3, collect some data. Conduct the experiment and collect some data. Step number 4,
Analyze it?
analyze the data. See if data supports. Supports what? Your hypothesis. Step 5 is make conclusions. It either supports it or it doesn't. If it does, then you're done. You're now famous. Right? You've proven your hypothesis. Nobel Prize in the waiting. What if the data does not support your hypothesis?
Start over.
You start over. You cycle back up to the beginning, and you revise your hypothesis, and you do the whole thing again. Well, you'll be relieved to know that in statistics class, we get to stop there. Whether or not it supports our hypothesis, we just make that conclusion. The data supports the hypothesis, or it does not support the hypothesis. As a statistician, you're not really in on that part of it. Scientists come to the statistician with a hypothesis. They ask for help designing an experiment. Then they go away and they conduct their experiment. The statistician's, again, not all that involved. Then they come back with their data. The statistician analyzes the data and tells them whether or not that data supports their hypothesis or not. That's statistical hypothesis testing. Okay? Now, just like the scientific method, there are 5 steps that we'll write out for conducting a statistical test of a hypothesis. The first one is identical. Only I'm going to say it a little bit different. Write out the hypotheses using mathematical symbols. The scientist won't have mathematical symbols. The scientist will say, well, I believe that when a star explodes, this happens, right? Or whatever their hypothesis is. But in statistics, we need to put that into something that we can rigorously test, and we do that by means of mathematical equations, right? And in statistical hypothesis testing, we have 2 hypotheses, whereas in the scientific method, they don't think of it that way. They have the same 2, but they don't think about it that way. And those 2 are known as the null hypothesis and the alternative hypothesis. And those are complementary events. What the heck does that mean, complementary events?
They complement each other. They're kind of the same.
Nope. It's almost, think of complement the same as it is in probability. The opposite of, right? So the opposite of. So basically, the alternative hypothesis is what must be true if the null is not true. Okay? Now, I got some information the other day about our friend Logan here. And he maybe has ESP. You know what that is? Extrasensory perception. He can read minds, right? But I'm a skeptic, so I want to test it. So I'm going to form my hypotheses that must be complements of each other. One of those hypotheses will be he has ESP. The other one is he does not have ESP. Which one do you think would go with the word null? What does the word null mean? None. 0, right? So no ESP would be the null hypothesis. So the alternative hypothesis is the opposite of that. So no ESP. The alternative is that he does have ESP. Right. Now, I still haven't written that out in mathematical symbols, but let's think it back to our scientific method. Design an experiment to test it. Well, the way I think I could test that is I'm going to flip this coin, and I'm going to think real hard on whether it's heads or tails. Okay, I'm thinking, and he's going to read my mind. Wow, he got it.
Well, it's not fair because it's 50-50 chance.
Well, what do you mean it's not fair? He just got it right. What you're telling me is that I collected some data, and that data was not enough evidence to convince you?
Yeah.
That's exactly the idea behind statistical hypothesis testing. We collect some data from samples, right? What I just did was a sample of size 1. And what have you learned about sample sizes? Bigger is better. 1 ain't enough, right? So just because he guessed right on the first one does not convince you. What would convince you?
Multiple times, or if he gets something other than something that only had 2 options,
Okay, so maybe I'd come in with,
a die maybe.
yeah, a 6-sided die, and he's got to
That
guess
would
which.
be better.
Yeah, then he's only got a 1 in 6 chance of getting it by guessing. Okay, better experiment. But even with the coin, I could devise an experiment that would give me strong evidence or well, strong evidence either way, right? Suppose I flip this coin 10 times, and I ask him to guess out of those 10, right? Guess 10 times. If he guessed 5 out of the 10 correct, would that convince you he has ESP? No, because you expect him to guess that many just by random chance, right? What would convince you?
All of them?
If you got all of them? If you got all 10? What if you got 9 out of 10?
Yeah, that's okay.
That's pretty good evidence, right? What about 8 out of 10? 8 out of 10, that's pretty strong. Well, how likely would it be that he could guess 8 out of 10 just by random chance? Well, now wait a minute. And I won't say just 8 out of 10, 8 or more. Because obviously, if you think 8 is strong enough evidence, then 9 would be stronger yet, and 10 would be even stronger. So let's say greater than or equal to 8 correct guesses out of 10. What's the probability of that? Probability that x greater than or equal to 8. Okay? Yeah, we'll have to figure that out in the calculator. We'll do that in just a second. What I want to do now is I want to write out those hypotheses in mathematical symbols. Right? So think of, I've designed my experiment. I'm going to flip this coin 10 times. And I'm going to have him guess all 10 of those, right? And we'll see how many of them he gets right. So in terms of mathematical symbols, if the null hypothesis is true, what proportion of the time would you expect him to get it right? Okay, now I purposely threw in the word proportion because I want to make this so it doesn't matter what my sample size is. Because here it matters. If this 8 depends on there being only 10. If I flipped it 100 times, then 8 wouldn't be the number you'd use, right? You'd use some other number. But if I turn it into a proportion, so 8 out of 10 would be 8/10, right? Then I can make a hypothesis statement about that proportion. What proportion of the time would you expect him to get it right? Well, remember, the null hypothesis means he does not have ESP, so he's just guessing, right? What proportion of the time would you expect him to guess correctly? Half. You got a 50-50 shot, right? So under the null hypothesis, and there's some statistical jargon for you, under the null. It means assuming the null is true. If the null is true, then the proportion of time that he guesses correct is 50%.
What's HO mean? That's the...
Yeah, and this is new notation. Capital H sub 0 is the notation for null hypothesis. The sub 0, 0 for null, or none. Okay? So null hypothesis, and this is proper notation. Okay? This is a P, not a P hat. I'm going to test a hypothesis about a proportion, but I don't put P hat in there because this is a population parameter. I don't have to do a test about P hat because I can look at what P hat is. I know its value. But what I don't know is the population value, so I have to do some hypothesis testing about that. Right? What's the alternative hypothesis?
0.8?
No, the alternative hypothesis was, and I erased it, but the alternative hypothesis is he does have ESP.
One. It would be
So how do I write that with P's? Now, you said 0.8, you're kind of on the right track, but if he does have ESP, he should get more than 50% correct, right? So that's our alternative hypothesis. P is greater than 0.5. Now that is known as a one-tailed hypothesis test. Now I'll explain what I mean by that in a second. The other ways it can be written is with a less than symbol. That wouldn't apply to this scenario, but or you could have a not equal symbol. All of these are considered the opposite of being equal to 0.5. Technically, the only one that truly is the complementary event is the not equal. But oftentimes we're not interested in the other side of the null, like in this case. If he has ESP, he should do better than 50%. If he does worse than 50%, I'm not going to be convinced he has ESP. Even if he does really worse, like doesn't get any right, I'm still not going to say, well, that means he has ESP, just in reverse. Doesn't make sense. Okay? So these two are known as one-tailed tests, and this one is a two-tailed test. And what that's referring to is the sampling distribution of p hat. So let me draw that here. Remember, the sampling distribution of p hat is centered at p, and it's roughly normal bell-shaped distribution, as long as you have at least 15 successes and 15 failures. In this case, I'm saying that if the null is true, that p is 0.5. Right? So I'm going to reject the null hypothesis if he gets far enough away from 0.5 to convince me. So I say, well, that's strong enough evidence. If he got 0.6, would that convince you? Got 6 out of 10? No, I expect to get 6 out of 10 fairly often. In fact, think about computing the standard error of p hat. If you go 2 standard errors, then that starts to become unusual. But before that, you say, well, that's not convincing evidence. So in other words, if I get a p hat that's out here in this tail, then I'm going to reject the null hypothesis. That's why it's called a one-tailed test. I'm going to reject the null hypothesis if I get out in that one tail. A two-tailed test would say, well, I'm going to reject if I get out into either tail. And that would be some kind of a scenario where you say, 5 years ago, the proportion of college students who drink was 0.6. And I think that now it's different. I'm not specifying that it's higher or it's lower, just it's different. That would be a two-tailed test. It either went up or it went down versus the null hypothesis of it didn't change. Okay? So one-tailed versus two-tailed test. So the scenario that we're doing with the coin flipping, that's a greater than 0.5. So proper notation. Capital H sub 0, capital H sub A for null and alternative hypothesis. Some population parameter, and then it's either equal to something or the alternative will let me start that sentence over. The null hypothesis will always have an equal sign in it. The alternative hypothesis will never have an equal sign in it. It either has a strict inequality or a not equal. Okay? Some of the homework problems will be worded like this. Is the statement given below a null hypothesis or an alternative hypothesis? In Canada, the proportion of adults who favor legalized gambling equals 0.5. Is that a null or an alternative? That's a null because it has an equal sign in it, right?
You said the alternative will have greater than, less than, or equal to, not equal to?
Right.
Okay.
How about this one? The mean IQ of all students at Lake Wobegon High School is larger than 100.
Alternative.
That's an alternative. Is it a one-tailed or two-tailed? One-tailed. It's a strict inequality, larger than 100. It was a question about a mean. What would the null hypothesis be for a means problem? I said make a mathematical statement out of the population parameter. What's the population parameter we use for means? Not x bar. X bar is the sample mean. What's the population mean? Mu. So null hypotheses, something like that for a means problem. Okay. Now I threw this mu sub 0, same thing here. This would be, in general, p equal p sub 0, where the p sub 0 is simply a placeholder for the hypothesized value. So in this problem, that's 0.5. We're hypothesizing that it's 0.5. So that's just kind of a placeholder. Okay? So hypothesized value, p sub 0. Okay? So let's do our test. Instead of just testing Logan, I'm going to test all of them. So what I want you to do is I want you to get it in the margin of your paper or whatever. I'm going to flip the coin. Then I'm going to think about whether it's heads or tails. And I want you to tell me what I'm thinking. So I'm thinking, ready? Everybody got your prediction? Okay, Morgan, what did you predict? Tails. Tails. Sorry, it was heads. How many people got it right? Wow, about half of you. Okay, I'm going to flip it again. Second flip. Write it down. What do you think it was? Garrett, what did you say?
Tails.
Tails, you got it right. Third flip. Write it down. Amy?
Tails.
Tails? Sorry, it's heads. Is this the fourth one? Write it down. Heads. Fifth flip. Tails. Sixth flip. Tails. What am I up to? Seventh? Seventh flip?
Yeah.
Tails. How many people got that one right? Only about a fourth of you. It's because you're expecting the heads because heads is due, right? What did we learn about that? They're independent. Doesn't matter what happened on the last flip. Next one. Got it? Tails. How many tails in a row is that? 4 in a row? What'd you write, Emily? It's heads. Broke the streak. How many was that? I need one more? Here we go. Tails. Now I want you to count up how many you got right. Now I'm going to convert your number correct into proportion correct by putting a decimal place in front of it. So the p hat that you could have gotten could have been 0 or 0.1, 0.2, 0.3, 0.4, and so on. And then we're just going to do a show of hands to see how many people got each of those. How many people really couldn't guess and got 0? Nobody? Okay. How about a 0.1? Anybody get 0.1? 0.2? Nobody got 0.2? 0.3? 1? Anybody get 0.4? 1, 2, 3? Anybody get 0.5? Just 2 of you?
3.
Sorry.
Oh, 3. 3? And then 0.6? 1, 2, 3, 4, 5, 6, 7. That's unusual. 0.7. 1, 2, 3, 4. 0.8. Nobody got 0.8? How about 0.9? Did I get all of them? Okay. What we have there is a really small set of p-hat values, but if you turn your head sideways and envision a histogram, what does that kind of look like? Bell-shaped and symmetric, right? Nobody got 0.8. This is a very rare class that nobody gets 0.8, but this is a smaller class than usual. This class is down to like 22 people or something. Usually 30 to 35 people, there'll be at least one in the class that gets 8 out of 10. In my last class, I had 35 people, and I had one person that got 8 out of 10 correct, right? That's why I have you all do it, because if I just had him do it, then I'm pretty darn sure he's not going to get 8 out of 10. Right? But where did we get this cutoff? How did we decide that 8 out of 10 would be sufficient evidence to reject the null hypothesis? Well, this comes down to something known as significance level. The significance level is the proportion of times we reject the null when it is actually true. Now in this case, I like this scenario of testing for ESP because most of us, maybe not all of us, but most of us probably don't believe that anyone in this room has ESP. Right? So we pretty well know that the null hypothesis is actually true. In practice, in real research, you don't know whether it's true or not. In fact, usually you believe it is not true, and that's why you're doing the experiment. You want to show that it's not true. The alternative is what you hope to show in almost all cases. Right? But here we pretty well know the null is true. So the significance level is the proportion of times that we would reject the null even when the null is true. And our brains are pretty good at coming up with a number that is close to that. Compute this probability for me using the binom CDF. You had to do this on the last test, right? Now, remember what to do with a greater than or equal? You have to do 1 minus and take 1 away, so x less than or equal to 7. So then that's 1 minus binom CDF at n is 10, because we flipped the coin 10 times. What's p? Well, if the null hypothesis is true, p is 0.5. And then a 7. Point 0.05. 0.55. Okay? And it's very interesting, and as a statistician I get this question a lot, well, how strong of evidence is strong enough? And what we do when we do a statistical hypothesis test is we put it into terms of a probability. What's the probability that we could have observed what we just did observe if the null were true? Because remember, we don't know whether it's true or not. But we can compute probabilities under the assumption that it is true. So it's a conditional probability. Condition on the true proportion being 0.5, what's the probability that a person could guess 8 or more correct? Well, it's not very likely. This significance level we call alpha, and we usually set it at 0.05. Which means there's a 5% chance that we'll reject the null even when the null is true. So we set our cutoff for rejection to give us approximately that probability of 0.05. So we kind of naturally, everybody said, yeah, 10 would be convincing, 9 would be convincing, 8 was kind of the borderline. That's where people said, well, that's where I started to think that, no, maybe not. And our brains naturally kind of go to this 0.05. So it's going to happen 5% of the time only. So if I had 100 people in this room, how many would I have expected to get an 8? 5. Right? So in a class of 35, I expect to get about 1, and I usually do. In a class of there's probably 25 of you in here, then 1 in 4, or 1 in 0.05 is 1 in 20, right? So I was still pretty confident I'd get 1 of you, but I didn't happen to in this class. But usually, there's only 18 in here? So expect 1 in 20, I only had 18. See, there's the problem. Okay, but this cutoff is usually set at 0.05. This is exactly the same concept as confidence level. This is 1 minus the confidence level, right? If I do a 95% confidence interval, that's the same thing as saying I have an error rate of 5%. 95% of the time my confidence interval will contain the true value, which means 5% of the time it won't. Well, that means I would reject the null hypothesis 5% of the time because 2 standard errors around my p-hat got far enough out that 2 standard errors missed the p in the middle. So this probability that we computed, and actually nobody in here had an 8, but let's say that somebody in here got really lucky and they got a 9. Right? We recompute, go ahead and recompute this probability. Hit second function enter and pull up the last thing you did and change that number to an 8 on the end. Yeah, and that would be an 8. .01. Okay. The probability based on what you observed in the data. So I'm pretending, suppose somebody got 9 correct, so that's data. The probability of getting data like you observed, or even further away from the null hypothesis, is called the p-value. Okay, so let me write that here. I shouldn't have erased that. Oh well. The p-value is the probability of observing data like our study, or even further from the null, further out in the tails, when the null is true. So if you really don't have ESP, what's the probability of getting data like you got, or even further from the null? So if somebody had gotten data of 9 guesses, 9 corrects out of 10 guesses, then the p-value would be 0.01. If the p-value gets less than your significance level, then you say, hey, that's pretty strong evidence. So you compare the p-value to your significance level. The significance level is set before you ever collect data, just like the confidence level on a confidence interval is set before you collect data. So I'm going to go collect some data, I'm going to compute a 95% confidence interval. That 95% has nothing to do with the data we get back. This alpha level, the significance level, has nothing to do with the data. It's just where my mind says, well, if they get past that, then I'm going to say the null must not be true. I'm going to reject the null hypothesis. Okay? So then we take our data and we compute the p-value. Well, what is the probability? Now for your class, the most anybody had was a 7, right? So if I compute this probability for a 7, then this becomes a 7, this becomes a 6, this becomes a 6. What is that probability? 0.17. Does that lead me to reject my null hypothesis? In other words, if you got 7 out of 10, is that enough evidence to say, ooh, they got ESP? No, because that'll happen 17% of the time just by random chance. What you want to do is you want to set your cutoff level at a point where it's very rare that this would happen by random chance. And that very rare in our minds is usually 0.05. Only a 5 out of 100 chance that this would happen. Right? So think about it like a clinical trial. If I'm testing drug A against placebo, there's a possibility that the drug has no effect at all. It's just like another placebo, but I happen to get a sample of people where I happen to randomize so that all the people that did good ended up on my active drug and all the people that did bad ended up on my placebo. That could happen, right, theoretically? And if it did, it would make it look like there's a difference, even though my drug really doesn't work. But how likely is that to happen? Not very. So I say, well, there's only a 5% chance that can happen. I set my cutoff for difference between groups so that that can only happen 5% of the time. And then I compute the p-value, and I compare it to that cutoff. And if the p-value gets less than 0.05, then I say, well, I'm going to reject the null hypothesis. And I'm going to say it supports the null, which means, wow, I think they have ESP, or I think this drug works. Okay? So, a lot of the homework problems are going to ask you things. They're going to give you p-values, and they're going to say, does this p-value support the null hypothesis? Well, right now, we don't know how to compute p-values. We'll learn that next time. But suppose I had a p equal 0.34. Oh, by the way, what does the p in p-value stand for? Probability. You now know more than most of the people that I do statistical consulting for. Because I always ask them, they always want to, well, what's the p-value of this? I said, why do you care what the p-value is? You don't even know what the p in p-value stands for. And they're, well, you're right. No, I really don't do that. That would be that'd be a way to not get consulting clients anymore. But that's what I'm thinking. Right? The p in p-value stands for probability. Right? It's the probability in the tail of the distribution. Right? The p-value can be thought of, this is not technically correct, but the p-value can be thought of as it's the probability that the null hypothesis is true. When the p-value gets small, then you say, well, it's very unlikely that the null is true, therefore I'm going to reject the null and accept the alternative as being true. If the p-value is big, like 34%, that's pretty big. Right? You say, well, it's fairly likely that the null is true, so I cannot reject it.
So what's the p-value for the experiment we just did, the 20?
Well, for those people that got a 7,
Right.
their p-value is 0.17. If somebody had gotten a 9, nobody did. But if somebody had gotten a 9, their p-value was 0.01. We computed that one a minute ago. What did you get?
Oh, I didn't do it because I was kind of lost on that.
No, I mean, how many heads, how many guesses?
I got 4 out of 10.
You got 4 out of 10. So what's her p-value? Well, probability that you could get 4 out of 10 or more. Right? Because we're going in a one-tailed direction, so I don't go away from the null in this case. Her p-value is going to be bigger than what? Bigger than 0.5 because she's on the wrong side of the null hypothesis, right? But if you want to compute it, that would be a 3, and this would be a 3. What do you get? Point what? 0.83. So what it's saying is that even if you don't have ESP and you're just guessing, then you could get data like you got, or even bigger, 83% of the time. Therefore, I'm saying, well, that's not evidence that you have
So you
ESP.
accept the null if it's bigger, and you reject it.
Now, what she just said, I'm not going to harp on this too much today, but I will in the next few days to come. She said, accept the null. And I don't have time today to explain to you why, but you can never say, I accept the null as being true. All you can say is, I fail to reject the null.
That's
Right.
with a high value.
Right. So I was starting to write that over here and I got sidetracked and I forgot. I'm going to go ahead and erase this. And we'll say small p-values support the alternative H sub A. Big p-values support the null. Again, we don't say the null's true, but it's, well, we seem to be supporting the null, so I can't reject that. Now, how big is big and how small is small? That's what this alpha level is. That's your predefined limit for how big is big and how small is small, right? So small p-values, p less than alpha. Big means p greater than or equal to alpha. Actually, I'm sorry, the or equal goes on there. A 0.05, we would go ahead and reject the null hypothesis. Exactly 0.05. But that never actually happens in practice. It's always 0.05 something something, or 0.04 something something. Okay? All right. So, here we go. We're going to work a couple of the practice problems, and these are going to be very similar to your online problem. And these are concept problems about hypothesis testing. We did a couple already about whether it was a null or alternative statement. So the next kind of a problem, for a new pesticide, should the EPA have the burden of proof to show that it is harmful to the environment, or should the producer of the pesticide have the burden of proof to show that it is not harmful to the environment? Give the analog of the null hypothesis and the alternative hypothesis if the burden of proof is on the EPA. So they use the word a pesticide being harmful or not harmful. In words, what's the null hypothesis?
Not harmful.
Pesticide is not harmful. Null means none or not. So the alternative
Harmful.
is harmful. Okay? Suppose the mean GPA of all students graduating from Washburn University is 2.8. The registrar plans to look at records of students graduating in 2005 and see if the mean has changed. Define notation and state the null and alternative hypotheses for this investigation. So that's this number one. Write out the hypotheses using mathematical symbols. My null hypothesis and my alternative hypothesis for this scenario. We want to see if the mean GPA, let me get the wording exactly right. See if the mean GPA has changed from 2005.
It has changed or it hasn't changed?
Those are my two hypotheses, right? Now, which is which? Either the mean changed or it didn't change.
Not changed.
Did not change would be the null. So now, how do I write that out with mathematical symbols?
MO.
First, what's the mathematical symbol for population mean? Mu. If it did not change, what's it equal to? What? 2.80. That's the mean it was back in 2005. So 2.80. This 2.80 is mu sub 0 for this problem. All null hypotheses have an equal sign. All alternative hypotheses don't. Remember that. Okay, so now what is my alternative? Okay,
Does not equal
all nulls, all alternative hypotheses will look just like the null, only with a different symbol in the middle. Now we just have to figure out which of those three symbols is it. Is it a less than, or a greater than, or a not equal? It's a not equal. Very good. It's a not equal because they didn't say, let's see if it improved. They said, let's see if it changed. And they didn't specify a direction. Okay? So if they ever say, is there a change, or are they different, or are they the same, those kinds of statements all lead to a not equal symbol. Okay? Here's one. I didn't talk about test statistics. He does that in the section. When you read the section, you'll see him talk about test statistics. But I saved that for when we get to 9.2, just because it's more than I can talk about in one lecture. But here's a question about test statistic, and we can kind of no, I'm not. I started saying we can figure this out, but I better not do that to you. I'm going to change it from being test statistic to a p-value question. Okay, so to test the null hypothesis that p is 0.5, that a population proportion equals 0.5. The test statistic is a z-score that measures the number of standard errors between the sample proportion and the hypothesized value, which is 0.5. If z is 0.36, do the data support the null, or do they give strong evidence against? So they say it's a z-score that measures the distance. So if you have a z of 3.6, that's 3.6 standard errors out into the tail of the distribution. So what's the p-value going to be? And instead of, I can't tell you what it would be exactly, but I know it's less than something. If I'm 3.6 standard errors out into the tail of the distribution, and I'm way out here, so that is 3.6 standard errors. P-value is the probability in the tail out past that. That's the definition for p-value. So what would that number be?
Less than 0.3?
Less than 0.003, actually less than 0.0015, because it's half of that, because it's 99.7% within 3, which means leaves 0.3%, and half of that's in the upper tail. So as a decimal, that's 0.0015. So does that support the null, or does that support the alternative? Would you reject the null hypothesis if you got a sample statistic way out there? Remember, the null hypothesis was 0.5. So this distribution is centered at the null hypothesis, and probabilities are computed assuming it was true. And then you make a decision, well, that must not have been true, or that is true. If you get a value out here, would that be convincing evidence that this distribution shouldn't be centered at 0.5? Yeah. So small p-values reject the null hypothesis. And how small is small enough? Less than your alpha level. Now they don't say what alpha level to use in this problem, and a lot of times they don't. So just like confidence levels, when in doubt, if they don't say, use 0.05. Sometimes we would make it smaller. We want a more stringent requirement for our hypothesis test, so we'll set it at 0.01. But usually it's set at 0.05. Okay? Any questions? Okay, I want you to write today's date down in your notes and say, we got out early. Because we're exactly 1 minute early. That's pretty rare for me. Have a great weekend. We'll see you Monday. Don't forget, tonight by midnight is section 8.4 homework. Don't forget to do that.